Hey, so this video is actually going to be a slideshow presentation. It's going to be a recreation of a presentation that I did recently for a graduate algebra course that I've been taking. So I just wanted to take a moment ahead of time and to sort of set the stage, really sort of talk about prerequisites for understanding this video. Of course, perhaps not all of these are strictly necessary, but the more of them that you have, the more comfortable you're going to be listening to this very condensed talk. So this course is centered around the theory of R modules. The sort of crowning achievement of this course is the classification of R modules over PIDs, although don't worry if that sentence doesn't make sense to you, because the content of my talk really doesn't involve that result. That's just to give you an idea of some of the work that goes into the background, some of the other things we've been talking about in this course. So an understanding of R modules is fairly important, or just some nice categories. That is to say, this book, though working on R modules, it's all doing it through the perspective of Aloufy's Chapter 0. So this is very categorically minded. We're talking about definitions in terms of universal properties, which I use in my talk, and we focus on things like homological algebra, cohomology, things like this. So I realize that's not very precise, but I'm hoping that gives you just a bit of an idea of some of the buzzwords you might want to know going in. So let's get started. So one thing I forgot to mention in the intro is that these slides are actually a slight permutation of the talk I gave in class, simply because I had, I had the suspicion that there was maybe a better arrangement of the slides, and based on some feedback, I think that might be true, but we're going to find out. So this introduction to derived categories is maybe a little different than the typical one. So the book we're using for this course, Aloufy's Chapter 0, is actually a pretty good introduction to derived categories if you want to have a hands-on understanding and be able to at least get your foot in the door and do some computations with them. But the reason why I'm giving the talk the way I am is because, as admitted in the text, he just doesn't have the time to properly introduce a derived category and how one goes about those definitions. So what I'm going to be doing in this talk is just giving you an idea of some of the ingredients that go into the proper definition of a derived category. If I was sort of making my own video from scratch, I might try and motivate derived categories from the way that cohomology appears in geometry, because I think that's a really rich and concrete way to get your hands on things personally. But in the context of this course, one thing that we've looked at already is some basic examples of what are called derived functors. So, for example, if we take the tensor product or the Hom functor, we can get the derived Tor or Ext functors. So to either introduce this to you for the first time, or to simply refresh your memory on what this means, if we want to define the ith Tor functor for a pair of R modules, M and N, so N is not on the screen yet, but it is going to appear in a moment. We define this by taking a resolution of M. So that means we take an infinite sequence of what are called projective R modules. So these are just some sort of nice examples of R modules in such a way that we have an exact sequence. So this first map is surjective, but more generally, each map in the sequence, its image is equal to the kernel of the next map. Next meaning in descending order here. What we then do is we take this other R module N that we have floating around. We then take the tensor product with N, and this gives us a new sequence of tensor products, which may no longer be exact by the failure of the tensor product to be an exact functor. And we measure this failure of exactness then with these R modules. So the ith Tor module of M and N is simply defined to be the ith cohomology of this new sequence. So one of the things you should be concerned with immediately here is, why is this well defined, right? I mean, you could take all sorts of crazy exact sequences leading into M, and somehow, like, if this is to be a sensible concept, it should not depend on this choice of resolution. And in fact, it doesn't, right? So that's a proof for another day. But then the question becomes, well, it seems like there's, at least from the perspective of derived functors, we don't really care so much about complexes and resolutions. We only care about them up to cohomology. So hold on to that idea, because it's coming back in a moment. More generally than R modules, we want to work in an abelian category. Now, if you don't know what that is, so unfortunately, in the context of the class I gave this talk for, one of my classmates gave a talk on abelian categories right before me. And so it's unfortunate we're not in the same situation. But abelian categories, first, let me just give you some examples. Namely, their namesake comes from the category of abelian groups. It's just a particularly nice category. And so abelian categories are categories which share some of those particularly nice features. It's not that there's anything commutative about them. So the sort of main features that we're, at least we're going to be interested in for this purpose of the talk, there's a lot of nice things about abelian categories, but the main thing is that kernels and co-kernels of maps always exist. Another great example of this is the category of R modules. Going forward with this idea of abelian categories, we would like to be able to talk about cohomology of chain complexes of objects of abelian categories. So to get the inspiration for what that definition should be, we're going to do something that seems maybe unnecessarily complicated at first, but let's notice that going back to our definition of the cohomology of some chain complex of R modules, the cohomology, the kth cohomology module is the kth kernel modulo the k-first image. But if you've spent any time working with co-kernels in, say, R modules, you'll have noticed they have a very nice example. It's just the co-kernel of a map is simply the codomain modulo the image. So in other words, this is just the co-kernel of the k-first image included into the kth differential. And we know that that's just an inclusion by the fact that we know we're working with a complex here. And so by exactly the same thing I've just said, we also know that the co-kernel of the k-first map is, as you see as I've written, and I just noticed a typo that superscript on the differential should be a subscript. And so what that means then is that the image, if we think about the map from the object to the quotient of the kernel, of course, the kernel of that quotient is precisely the image. And then again, by what I've just said, we see that that projection map is really the k-first co-kernel. So why am I saying all these complicated kernels and co-kernels? The thing is, if we now assemble all these pieces together, we see that the kth cohomology can be written as the co-kernel of the map from the kernel of the co-kernel to a kernel. And all this complication, the point being is now we've just rewritten everything in terms of kernels and co-kernels. And that means that this definition now works in an arbitrary abelian category. So great. Now we can work much more generally. So just to go back to this point of the fact that we really only care about complexes, sometimes we really only care about them up to cohomology, we're going to define a quasi-isomorphism is just going to be a map of chain complexes that induces an isomorphism on each of the cohomology groups. Now, your first concern might be, well, is this a worthwhile definition? I mean, maybe the only quasi-isomorphisms are ones that are isomorphisms of complexes. So here's an example to show you that no, it's not. So I'm not going to go too deep into the explanation, but if you pause the video and think about it for a moment, you should see that both of these above, we have if everywhere is a zero map except for this projection map pi, we have a morphism of complexes. And if you think about the cohomology, I mean, it's zero everywhere except for the slot where the pi is. And it's going to be equal because this is just the multiplication by 2 map above. So this map induces an isomorphism on cohomology, but it is clearly not a bona fide isomorphism. I mean, the only map going back up in the other direction for this one slot of interest here is just the trivial map. So it's clearly not going to be an isomorphism. Okay, so the question then is, so we've come to the conclusion, we care about abelian categories. Sometimes we only care about chain complexes up to quasi-isomorphism. So, you know, lots of times when we realize something in mathematics, there's all this data, and then for certain reasons, we only care about some of it. We take a quotient then at times. So we can quotient out this category, or rather the question is, can we come up with a definition of quotient for a category that allows us to identify quasi-isomorphic objects? You know, this may give us a simpler description of things if that's all we really care about. Now, you'll notice one of the first sort of barriers to this is, you know, normally when we think about quotients, we think about equivalence relations. So typically we need some sort of symmetry. And as I've just highlighted, there's no obvious inverse map in this example that I've written down. So we're actually going to use the idea that sometimes it's easier to formally invert stuff than it is to, well, you'll just see. So one of the things that's great about category theory is we basically can just pull a Mr. Bean every time we're looking for the right definition, right? So one of the things that's been discussed in this course is the idea of a localization of rings. Now, why am I bringing this up? Well, if we think about what we're trying to do here, right, we're trying to create formal inverses of certain maps. And so if you know a bit of category theory, you might say to yourself, well, there was somewhere else I was trying to create formal inverses this other time. And you might think about, oh yeah, when I took the field of fractions of an integral domain, or more generally, if you localized a ring at some sort of multiplicative set. Because what you're doing, right, is for all the elements S in this multiplicative set, big S, you're creating a formal inverse, 1 over S, for each of those elements. And if you happen to go through this exercise and discovered the universal property, so that says where we have this just standard inclusion map, which takes an element R and maps it into R over 1 of S inverse R. And it satisfies the universal property that for all ring morphisms from R to S, such that the image of any element from S is an invertible element, then it factors uniquely through this localization. So then what you might be thinking then, what you might guess, take this as your guiding light for the right definition of a localization of a category. So if you had some sort of, say, collection of morphisms W that you want to localize at, first off, you should have some sort of natural inclusion functor. And you should also, you know, the sort of copycat universal property is that if for all functors such that each morphism in this class W is invertible, that is an isomorphism in the target category, then that functor should factor uniquely through. Now, I'm just going to go a bit more directly, but say if you're taking an explorative approach to this is the beautiful thing about category theory. Sometimes it allows you to guess the right definition based on universal properties from other objects. Okay, so in order to formally invert some of these elements, recall that a locally small directed graph is a class of vertices together with a set of ordered pairs of those vertices. And so we actually then, under this interpretation, we actually have a functor from the category of locally small categories to the category of graphs. So if we think about, you know, what do we have? We have all the structure in a given category, right? The sort of main thing there is that we have morphisms and that we can compose them in some sort of, you know, associative way. But there's all this extra structure too, right? Like there may be like kernels and products, or you might know that they're linear transformations or continuous maps or something. But you could just sort of think about this collection of dots that you have, which are objects, and so the morphisms is just being arrows between them. And so if we forget that category structure, we actually get a functor from the category of locally small categories to category of locally small graphs. Oh, I should remind you, a locally small category simply means your morphism sets are on the order of sets. So that's why we're allowed to define this functor, which just takes our isomorphism classes of objects, treats those as vertices, and then each morphism just becomes a directed edge. Now, there's a general mantra with functors is typically, if you have some sort of free functor and you have some sort of forgetful functor, they will be adjoint to each other. So the fact that we have some sort of way of forgetting objects in a functorial way should make us suspect that there's actually another functor going in the opposite direction lying around and that it's adjoint. Sure enough, it is. So what we do, this functor P going in the other direction, it takes vertices and now treats those as objects of the category. And now morphisms are composable, passive composable edges. So if you have an edge, of course, that's going to be a morphism, but maybe you have two edges so that the head of the first edge is at the tail of the next one, and that composition would also be a morphism. Now, our directed graphs may not necessarily have loops on all the vertices, and we do need, by the axioms of a category, some identity morphism. And so here we're simply going to define the empty path to be the identity morphism. Okay, so on this sort of path of trying to invert, quasi-isomorphisms or just some collection of morphisms. Now, you'll notice on the screen, this isn't really the best notation. It looks like I've written W as a subset of the morphisms of the category. I suppose here I should explain myself. C0 is typical notation for the objects of a category, and C1 is typical notation for the morphisms. So this certainly may not be a subset, right? If we think about all the morphisms we're inverting, this, even though between two objects the morphisms are a class, all the morphisms we're inverting by could form a proper class as well. So we're going to define a graph U sub W of G to have vertices, which are just given by the objects of our category C. And our edges, of course, are given by all the morphisms of our category. But now, remember, we also want to, so that's automatically includes all our morphisms W, but now we want to make sure for each of those W, we want to create a formal inverse. So if we have a directed, if we have a morphism going from an object here to an object here, what we're going to do is just formally add an edge going in the other direction. And now this is easier to do in sort of this world of graph theory where things are like locally small and we think about formal elements of sets, and we're not having to sort of worry about some sort of category structure. That's why we pass to this category and do this formal inverse here. But now we have this adjoint functor going in the other direction. So once we've used the graph to formally invert these elements, now we can go back and we define PCW to be the image of this locally small graph under this functor P. But there's a problem, right? You might be thinking, oh, well, we're done, right? We formally inverted something in our category and we've passed back and that's the end of the story. But the problem is, recall that we defined through this functor the identity morphism to be the empty path. And the problem is that the empty path is certainly not the same as some sort of loop. And so if we follow through all these definitions, what would have happened is that the category we started with would have given us a loop in our graph, but now somehow that loop coming from the identity morphism is not identified with the identity path. So somehow we need to collapse this. We want these to be identified with each other. because of course we still want to represent the original structure of this category. So here is a theorem then. We now want to ask ourselves more generally, what does it mean to take the quotient of a category? So suppose C is a locally small category equipped with an equivalence relation for each pair of objects, X and Y. Furthermore, we're going to suppose that if we have two morphisms which are related by one of these equivalence relations, then we're going to just suppose that we can both post and precompose these morphisms. And this should be sensible in the idea of category theory, right? What do we have? We have objects, we have morphisms, and what's the main structure we're concerned with? It's the composability of those morphisms. So certainly we should respect that. So given this whole setup, then there is a category, which I'm going to call C bar, whose objects are exactly the same as the objects of C, and whose morphisms are quotients of the individual morphism sets by this equivalence relation. And then finally, we should have, if there's any sense in this world, suppose we have the class of represented by F and the class represented by G, then we're simply going to give a defined composition as the class of F composed with G. And finally, there's a full functor, meaning simply it's surjective on all of the sets of morphisms from this category down to here, just as we, typically in the world of sets, if we have a set modulo some equivalence relation, there's this surjective map. So this is kind of the surjective analog. So there's really not a lot to check here if you trace the definitions. I mean, we have a category. What do we need? Identities of objects. It shouldn't be too hard to convince yourself of that. Really, the only serious thing I would say, I mean, it's all worth checking, but the real only serious part of this proof, I would say, is just that this composition is well defined, right? Because we're talking about equivalence classes. So to check that, I mean, suppose we have F and G, which are related, and H and K, which are related. Well, by our assumption, we know that we can post-compose maps and preserve equivalence conditions. So we get this first line here that HF is equivalent to HG. But we also know that we can pre-compose maps, again, by our assumption. So we know that H of G is equivalent to K of G. Well, now you simply stitch these together and you find that HF is equivalent to KG. So in other words, the composition of the class represented by H and with the class represented by F is by definition the class of H composed with F. And we've just seen that that is the same as the class of K composed with G, and that is the class of K composed with the class of G. So our composition does not actually depend on the choice of representative. And so finally, just to tell you, I mean, again, verifying these functorial properties is a great exercise to do on your own and basically immediate, where our functor, of course, is just the identity on objects, and then it sends a morphism to its equivalence class. And sure enough, as a sanity check, right, if this is going to be a bona fide quotient of objects, you should go ahead and check that that it satisfies some sort of analog of the quotient property. Again, I would suggest go look at the property of the universal property of quotients for abelian groups, or the universal property of quotients of modules, and just compare it to what I've written on the screen here. And it somehow has the same sort of sense. So if you didn't know the definition of a quotient of a category before, you might somehow be led to this by understanding definitions of quotients in other categories. Another Mr. Bean moment. Okay, so finally we've defined this this image, or we took our category. We built a graph. We then took this adjoint, the image of that graph under this adjoint functor. And so finally, now that we know what equivalence relations are, we're going to define an equivalence relation which identifies the empty path and the class of the original identity morphism from our category. we're going to say furthermore, so this sort of natural identity should extend, that any two classes are the same if and only if any of the representatives being compositions of maps of possibly different lengths, but they have to literally be the same map. And then, of course, we want it to be the case, right? We're sort of mimicking this definition of the localization of rings, right? So the element S over 1 is the inverse of 1 over S, but you sort of have to take a quotient to make that happen. So we're also going to do that here, right? We're just going to make sure that the class of WW inverse is the same as the identity, and same with swapping the order. So making sure that these are literal inverses to each other. So taking the equivalence relation of the previous slide now for a locally small category C and any collection of morphisms of our category, the localization of C at W is defined to be this PCW modulo the equivalence relation from the previous slides. So it turns out then, theorem, really, this is a theorem definition, that, the objects are just the, if you trace through basically everything I've talked about so far, the objects are simply the objects of the original category. There is a functor, which just acts as the identity on objects, and to act on morphisms, you just sort of have to follow out these other functors. And it does this in such a way that for all S in W, the image of S under this functor is an isomorphism in the localization. And sure enough, in fact, it follows, it satisfies this universal property that we discussed earlier. Okay, so you might have noticed in the last whole chunk of time, I've been talking about categories in general, but the whole reason we started on this business is because we realized we wanted to identify quasi-isomorphic complexes of abelian categories. So finally, we come to the proper definition of a derived category. So that is, given an abelian category A, we define the derived category of A to be this localization of the category of chain complexes of A, where W is the collection of quasi-isomorphisms. And so now, if you go through, I wanted to remember the whole point of this was to simply show you some of those ingredients that go into the full and proper definition. Perhaps a more intuitive talk that allows you to start working with derived categories will generally work up to these things and prove lots of useful theorems in between. They'll talk about these different flavors of what are called bounded derived categories, and also the homotopy category. So we think about chain complexes, but we also consider these sort of homotopy morphisms. Again, this is why I mentioned it's good to know some geometry, because what's a homotopy of like R modules or something? Well, the inspiration comes from understanding like cohomology in more geometric settings. So I would defer to Alufi to look at this, because if you follow through all these abstract definitions just as we have, but you don't prove any sort of nice theorems about ways of representing and understanding these derived categories, it can sort of be a nightmare. And they're not always as bad as simply just doing that. Another big thing to talk about here is triangulated categories, right? This is a very important topic as well. And you might wonder, for example, we started with an abelian category and we did all this fancy magic, and abelian categories are nice. So you might hope, well, did we get an abelian category back at the end of the day? And sadly, the answer is no. But we do still have some sort of nice structure, and that is the structure of a triangulated category, which I'm not going to go into today. But while our derived categories may fail to be abelian, and they may fail to be, but still triangulated. In some cases, there are nice abelian subcategories. So in the case of if we have a complex algebraic variety, in fact, this might even be more general. And I apologize if these words don't make sense to anyone. There is a notion of what's called sheaves. And they form a category. And it turns out, if you take this certain bounded derived category of sheaves on such an object, and in fact, you definitely can do it more generally than a complex algebraic variety, but for the immediate next point I'm going to make, I believe it does have to be complex. But there exists a very nice subcategory, which is called the category of perverse sheaves on this object. And the reason I wanted to just name drop these at the end of my talk on derived categories is for two reasons. So one, well, sort of one reason, it's a point of contact between the instructor I had for this course and my personal research. So the instructor for this course works in the theory of D-modules. And in the theory of D-modules, there's this nice theorem called the Riemann-Hilbert correspondence. And it says that understanding these certain kinds of D-modules, which form a category, it's actually equivalent to the category of these perverse sheaves. And then, so I don't really have time to go into the details that I still don't fully understand about how they arise in my research. I mean, these seem like very complicated abstract objects, and they are. But the surprising thing is that somehow if you loop around this abstract, complicated world, at the end of it, you can sometimes actually just get to some nice combinatorics, which allows you to parameterize the things you really care about in some simple combinatorics on these perverse sheaves. So thanks for sticking with me through all of this and listening to my talk. If you have any questions, leave them in the comments below. I'm very happy to take any questions, and you know, definitely welcome corrections, because I'm still pretty new to this world as well. So thanks.